Hello viewers, my name is Metaliron. In this lesson we'll be looking at the topic iron. When you look at iron, it is the most important element. Virtually everyone knows iron, and it is the second most abundant element on the earth crust after aluminium. Aluminium is the most abundant metal, but iron is the second most abundant metal. If you want to see the iron is mostly found in form of ores, which are called hematites. And looking at the hematites, the symbol, the chemical formula is Fe2O3, that's iron 3 oxide. We also have magnetites, which is tri-iron tetraoxide. These are the different forms or the ores of iron. We also have what we call siderite or spatic. This is FeCO3, that's iron triazocarbonate 4, iron 2 triazocarbonate 4. That's the siderite or spatic, is another ore of iron. If you want to remember, just like football club FC, then spatic sounding like sports. Once you remember spatic sports, that's football club, iron 3, iron 2 triazocarbonate 4. Another ore of iron is iron pyrites, which is iron 2 sulfide. We also have limonite like lime. Remember lime water. Once you remember lime water, it means you remember H2O that is here. So then Fe2O3, the common iron pyrites. Just join the common iron pyrites with H2O to remember limonite, lime. So iron 3 oxide, trihydrates. So these are another ore of iron. Iron is widely present as triazosilicates 4. That means the place where they see iron, you see it as a triazosilicate, meaning that it's full of sand or silica, especially in clay soils. How do we extract iron? Remember, the ore of iron is hematite, and we can use coke. Coke is carbon. Carbon is a good reducing agent. What will it do to the hematite? It's going to remove oxygen from it. And once it removes the oxygen, it will become carbon 4 oxide. So, and that process is a kind of exothermic reaction whereby there will be a great heat that will be needed to heat up another substance needed in extraction of iron, which is limestone. Don't forget, to start with, you take hematite, iron 3 oxide, of which carbon, coke, will be used to remove oxygen from the Fe2O3. So that the O will join with the carbon to form carbon dioxide, which will be a great exothermic reaction causing more burning in the furnace. And that more burning will now break limestone into calcium oxide and CO2, such that the calcium oxide will be used as to take up silicon oxide, the silica, to form a slag, which is the waste or the impurities, while the remaining CO2 will be reduced again by more carbon. If the carbon is added the more, it means the remaining CO2 of this limestone will be reduced by that carbon into CO. And that CO is now the major reducing agent that will now finally remove the oxygen that is in the hematites to remain ordinary iron. And take note, air is also needed in extraction of iron. That air is the combustion substance, the one that will be burning in the furnace. Now let's proceed. Hematite is basically iron oxide, and oxygen must be removed to leave the iron. That means we call it reduction. So carbon is one that will do the work, and carbon is more reactive than iron, meaning that if iron is stick to oxygen as iron oxide, carbon will take over. It will take the oxygen from the iron because it's more reactive. Then it can displace the iron from its oxide. Hence, the method for extraction of iron is called reduction by carbon. Now, this is the blast furnace where the extraction of iron takes place. The first thing, take your iron up, which is the major material needed. That's the iron 3 oxide. Add it, you pour it into the blast furnace. Once you pour it there, you also pour your carbon, that's the coke. What will the carbon do? So its aim is to come and reduce this iron oxide. Then you pour your limestone, and I told you this, the oxygen, there's another oxygen apart from the oxygen that is in this iron oxide. There's another oxygen which will be passed from here. They call it hot air hot air blast, that's oxygen. So that oxygen, as it's coming up, so it can go and meet up with the carbon that is coming from the top. So the carbon from the top, oxygen from the base, they will form carbon dioxide, which is an exothermic reaction that will make the burning process increase in this blast furnace. Then the carbon, if it keeps coming, it means out of the carbon dioxide, CO2, it will be reduced to CO. And that CO, what will it now do? The CO is now the one that will reduce the iron ore. That means the CO will remove out of this iron 3 oxide to leave iron alone. So that is how each of them works. Then there is a gas that will be wasted. So that means any impurities that is found in that furnace will be coming out in form of gas. And take note, from the limestone, apart from the the heat of the coke, air, carbon, and the oxygen from the ore, so that CO2 from this limestone, remember the CO2 is a kind of exothermic reaction, the heat. So meaning that heat has the power to break limestone into CaO and CO2. So the CaO is now the one that will take up the silica. So any silica that is there, so it will pick up the silica and then form a slag. So this is where the slag will be. So tap O for slag. So we have the slag here. So the slag will be here. That's where we have our calcium, the silicon, and the oxygen. So that's calcium. So that's the slag that will be formed. So this CaO is from the limestone, then the SiO from the silica, that's the sand. So it means it will be molten, it will melt by the high temperature from the top. So it will melt it and stays here because its density is not as high as that of iron. So after iron also has been reduced, iron is also coming down so that it can be trapped off from this place. So that's the blast furnace. All I've explained will just be repeated here, that the iron ore, which is the iron oxide, the coke, which is the carbon, the limestone, all of them will enter the blast furnace at the top. The hot waste gases at the top of the furnace are piped away and used to heat the air blast. That means like the carbon dioxide. So at the bottom, so coke is impure carbon and it burns in the hot air blast to form carbon dioxide. So this is strongly exothermic. So I've said that, which makes it an important reaction. It helps heat up the blast furnace. So you can see how the carbon is joining with the oxygen to form carbon dioxide, which is an exothermic reaction. Now that carbon dioxide we say to be reduced by carbon. If you keep adding carbon dioxide will be reducing to carbon monoxide. So what will you now use this carbon monoxide for? So the carbon monoxide is now the one that will go and meet the iron oxide, that's the hematite, and reduce it to ordinary iron, so that the CO will increase to CO2 by picking oxygen here. So due to high temperature, the iron produced will melt. It will melt and it will be flowing at the bottom where you are going to tap off that iron as our product. Then another thing we need to know is that limestone, I've also said all this, I've actually said it, but just for you to have the note, the limestone is added to the furnace to remove impurities. So how will it remove impurities? That's by thermal process. It will first break by heat, so it will decompose into calcium oxide and carbon dioxide. So this is an endothermic. Take note, the formation of calcium oxide and carbon dioxide is endothermic. That is when it is breaking, so heat is absorbed. And this one we must be careful not to add too much limestone. If limestone is too much, it means there will be too much endothermic. That means the environment will not be as hot as it ought to be. So therefore there will be cooling. So it will affect some other reaction. So this limestone giving CaO and CO2 is an endothermic reaction. And take note, calcium oxide is a basic oxide. So it will be looking for an acidic oxide, which is your silicon oxide, the sand. So once the silicon oxide, the acidic oxide, and the calcium oxide, which is basic oxide, once they come together to give us the slag, which is calcium trioxosilicate. So that's the slag. And I've said the molten slag it will float when you melt it. So it will float on top of the iron. It will be less dense. You tap it off and the iron also is tapped off. Now what do we use iron for? We have different iron. We have cast iron, we have mined iron, we have wrought iron, high carbon steel, stainless steel. So what are the usefulness of all this before we round off this topic. The first thing, when we say cast iron, before we get cast iron, we must have gotten pig iron. What is pig? Something that is dirty. Pig is a dirty animal. Immediately from the furnace, the first iron that comes out from the furnace is called pig iron, because it's still dirty or it's not fully pure, though it may be pure but not perfect, so we call it pig iron. But if you now still go and melt it again, that pig iron, and then you break it and cast it into a mold, then you can say that's cast iron, because you have cast it into a mold where it will form a new shape. So, and that kind of carbon, now there are some things we need to know about it. It's still somehow impure. That cast iron, even though you have remelted, you have cooled, it's still having little impurities, about 4%. So, and that's why this cast iron, though it's still very hard, it's still very hard. So because, and again, it's very brittle, that means it can break, because there's still impurities there, so it can still break and tend to shatter just like glass. So instead of bending, instead of experiencing flexibility, will rather shatter because of the impurity that is still there. And that's why they can just use it for blocks in car engines. Then the next one is mild steel. When you say mild steel, this one, it has just small amount of carbon. So the small amount of carbon increases the hardness. So it means when the carbon is not that much, so it means it will be more, it will be harder. So that's, the iron will be harder, and that's why we can use for wire, for nails, for car bodies, for ship building. So any iron that the carbon is not much at all is a mild steel. Just like when you say a mild punishment, that means little punishment. So the same with mild steel, very low carbon is there. So you can use it to do to construct ship building, car bodies, etc. Now, wrought iron. This one is now the pure iron. You can use W to remember that, W, water. So your water is pure water. So from the word water to water, pure iron. So this one now, instead of being hard, it will be soft because it's pure. So, but it is the one that is having impurities that become stronger. So it's like what gives strength is different things that come together. But if there is no combination, it will be somehow soft. So, and that's why they don't use this kind of wrought iron for structural purposes. Now, high carbon steel, there's something we call steel. Steel contains carbon. So if carbon is too much in your steel, it will increase the carbon content, so it makes the iron become harder again. So mean that carbon is what makes your iron hard, and that's why you can use this one for cutting tools for your nails. So the nails you use for your concrete, so that is for the high carbon steel. Then we have stainless steel. So many people have stainless maybe plate, stainless materials. So this stainless steel, what does it have? Is an alloy. That stainless you see is an alloy. You know, there is a kind of stainless like this. So this stainless steel is an alloy. You see one folded part under it here. So it means it has iron around it, and it has chromium. So you can say this is letter C from the drawing of the stainless. So chromium. Then it has nickel. Nickel, you can say from here N. So you can say chronicle. So nickel and chromium. So nickel and chromium. So that's stainless. So the chromium, the nickel, they are all in your stainless steel. So chromium and nickel, they will make it form strong oxide layers, so they can protect. So stainless is protecting against corrosion. So stainless doesn't easily get rust because of the chromium and the nickel that I've added to it to form your alloy. You can also use it for your kitchen saucepan, your knives, your fork. So all these are for your stainless. So your stainless steel. So with this, we have looked at iron. Thanks for. Okay, before we proceed, before we round off, we are here to look at physical properties, the chemical properties of iron. So physically, when you see iron, what are the things you can say about iron? If the iron is pure iron, the color will be gray, and the density is 7.8. It can melt at 1535, and it can boil at 2800. Meaning the iron can turn to liquid. So that's at temperature of 2800. Then it's very malleable as iron. Remember that metals, most of them are malleable. You can hammer them. They are ductile. You can draw it to wire. Good conductor of heat and electricity. It can easily be magnetized. Iron can be attracted by magnet. Now, chemical properties of iron, meaning that when you add iron to some chemical elements or substances, what will happen? The first thing, you can add it to the chemical element called oxygen. So it will form, and take note of the oxygen. This oxygen is from the air, and inside the air there is water, and that's why the compound that will be formed will be a rusted iron. So that's a rusted iron, meaning that iron that has water, so it will be formed when it is exposed to air, or you call it hydrated iron. You don't want to say rusted iron, so hydrated iron, because it's getting oxygen from the air and water, so hydrated iron. Now, when finally divided iron is heated in air, it will burn at high temperature to form magnetic iron oxide. Also, another one is steam. When you take steam, that's hot water. If you add it with iron, so it will produce tri-iron tetraoxide, and hydrogen gas will be liberated. So that means that water is acting like an acid, where iron in an acid is now trying to liberate hydrogen gas. So because iron is higher than hydrogen in the electrochemical state, so it means iron is trying to liberate hydrogen gas, so acting as a metal, while water is acting as an acid. So, and take note, this says steam, so that means it's more powerful. So that's where we stop for today. Thanks for listening.